Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about neural networks and deep learning. Neural networks are complex nonlinear models that can be used for regression or classification. Deep learning refers to the approach of fitting large neural networks, very deep neural networks, to large amounts of data. In the last 15 years, this approach has been spectacularly successful in many applications, including language modeling, computer vision, speech processing, and others. In fact, a lot of my research is about designing deep learning models for medicine, climate, and imaging. I have been consistently amazed at the ability of these models to to learn complex information directly from data. In this video, we're going to describe neural networks for regression and classification from first principles and then explain how to fit them to data. Let's get to it. We're going to talk about neural networks and deep learning, and we're going to start with the problem of regression, where we want to estimate a quantity called the response from multiple features. In our video on the conditional mean, we explained that there's an optimal estimator, which is the conditional mean. But the problem is that unless our number of features is very, very small, it is in general intractable to compute the conditional mean from data due to the curse of dimensionality. Essentially, there's too many possible combinations of features to be able to just learn a conditional average naively from the training data, because then when you apply your model to new data, you're probably going to see different configurations of features. And this is essentially the curse of dimensionality, which we have talked about at length in other videos. So because of this, we have to make assumptions when we solve the regression problem, and a very popular assumption is linearity. In linear regression, we assume that the response, which we denote by y, is approximated as a linear function of the features x. So this is what a linear regression model looks like. Realize that there's an additive constant here alpha, so in reality this is actually an affine model. The important thing to realize is that the response increases or decreases proportionally to each feature if we fix other features. So this is governed by these linear coefficients that are multiplying each of the features. That's a fixed constant linear coefficient that is multiplied to each of the features. Of course, the coefficient is different for each of the features, but it remains fixed and does not change depending on the actual value of the feature. As we will see, this can be quite problematic because it does not allow us to capture nonlinear structure in the data. In order to illustrate that, we're going to use the same data set that we used as a running example in the video on regression trees and the video on tree ensembles. In this example, we want to estimate the temperature in Manhattan, Kansas, that's our response, from two features. The hour of the day, which is a number between 0 and 23, and the day of the year, which is a number between 1 and 365. Our training data are temperatures from 2015, and our test data are temperatures from 2016. This is what the training data look like, and this is what the test data look like. So realize that the structure of the training data and the test data are very similar, but there are different fluctuations year to year, and we want to build a model that is robust to these fluctuations. What we realize here is that this is the day of the year. At the beginning of the year, during the winter and spring and beginning of the summer, temperatures rise steadily. And then after the middle of the summer, they start decreasing again. If we look at the dependence of the temperature with the hour of the day, something similar happens, where in the morning and the beginning of the day, like in the night and the morning is what I meant. So this is the night and this is the morning. During the night and the morning, temperatures rise, but then in the afternoon and evening, they fall again. Why am I bringing this up? Because this is clearly a nonlinear pattern that a linear model is going to have trouble capturing. In fact, it cannot. So let's take a look at a linear model fit to the 2015 data. The problem the model has is that it has to choose a fixed linear coefficient for each of the features. So it cannot first grow with respect to the hour and then decrease with respect to the hour or with respect to the day. And this is what the resulting estimator looks like. The model needs to choose a fixed constant for each of the features, and what it does is it chooses a pretty small constant, because what it would really like to do is to, for example, with respect to the day of the year, grow here and decrease here, but it cannot. It has to do the same throughout the whole year, and what it does is like grow very, very slowly. This does not provide a good fit to the data. I'll just reiterate that point because it's very, very important. The response increases or decreases proportionally to each feature, and for this data set, that's a big limitation because of the nonlinear structure within the data. In particular, the nonlinear dependence between temperature and hour and temperature and day. And because of that, this model has terrible training error, 10 degrees, and also terrible and similar test error. So there's severe underfitting here because the linear model is not able to capture relevant structure in the data because that structure is nonlinear. So our challenge here is how to learn a nonlinear model that is able to capture that structure. And the way we're going to do it is with a neural network. Neural networks interleave linear layers, which are linear transformations, and nonlinearities. In order to explain this more clearly, we're going to look at a specific example. We're going to take a network that has been fit to the 2015 data in our temperature estimation model, and we're going to analyze it. Later on, I will explain how the parameters of this network were learned from data. But for now, we're going to assume they are fixed, and we're just going to analyze what the network does. So let's start with the first linear transformation or linear layer, where we obtain some hidden variables by performing linear combinations of the input features. So here, this is the hour feature and this is the day feature. What we do is we multiply the day by a certain linear coefficient and the hour by another linear coefficient, and then we add an additive constant, and this gives us the value of this hidden variable. Usually, we compute a lot of hidden variables in each layer. Now we're going to have a very simple network that has just two hidden variables. The second hidden variable is obtained with a completely different linear combination of the input features. In particular, look at the difference between this coefficient and that coefficient. Okay, it's completely different to the other one. Again, linear coefficients are applied to the two features, and then we have an additive constant, and this gives us our second hidden variable. So now we have two hidden variables that are linear combinations of the input features that are different. Before thinking about how to combine these hidden variables into a final estimate, we have to introduce a key step, a key feature, not feature here is not a key property, or like a key element. I like element better. A key element of neural networks, which is the nonlinearity or activation function. What I skipped here, and sorry about that, is that these are actually parameters that are learned from data. Okay, these linear coefficients and this additive constant, the linear coefficients, we can put them in a matrix W1 and the constants in a vector alpha 1. These have to be learned from data, and we will talk about that a little bit later. Okay, so this linear transformation of the input features gives us these two hidden variables, and as I was saying, now we come to like a crucial element of neural network, which is the activation function or nonlinearity, which is applied separately to each hidden variable. And it's almost embarrassingly simple. At least this one that I have chosen to show you. Others, there's other possible nonlinearities that you can apply. The most popular ones are all kind of similar to this one, or many of them are similar to this one. The rectified linear unit, which is one of the most popular nonlinearities, all it does is it sets negative entries to 0. If it sees that the hidden variable is equal to -1, it will set it to 0. Otherwise, if If the value is positive, it just leaves it alone. That's all it does. So let's include this in our neural network. Here we have the hidden variable that is this linear combination of the input features. When it goes through this ReLU nonlinearity, what happens is that if h1 is negative, it's set to 0. If it's positive, it's left alone. Okay, and the corresponding rectified hidden variable is denoted with this little plus here. The same happens to the second hidden variable. It goes through this ReLU. Oops, sorry about that. That looked kind of weird. It goes through this ReLU, and if it's negative, it's set to 0. If it's positive, it's left alone. And this gives us these two rectified hidden variables that we're then going to combine to produce our output. In more complicated models, there would be more hidden variables and more layers. But here, I want to keep it simple and also be able to show it in a slide and then analyze how this model works. So we're just going to have these two rectified these two rectified hidden variables that are combined to produce the output of the model. How are they combined? Very simple, another linear combination with an additive constant. So we take the first rectified hidden variable and we apply a linear coefficient that is also learned from the data. Another linear coefficient is applied to the second rectified linear variable and we add a constant. And that's it. This is the whole network that I wanted to show you. Again, these are parameters, these two linear coefficients and the additive constant that are learned from data, as we will explain in a moment. Great. So now let's think a little bit carefully about why this makes sense. Why is this achieving what we want? In order to do that, we're going to study what is the function that is actually implemented by the neural network. And what we have to realize is that at the end of the day, it's an affine transformation, but the very important thing to realize is that it adapts to different values of the inputs, which is something that a linear regression model cannot do. And the reason that it adapts to different values of the inputs is that the ReLUs are going to be activated depending on the inputs. And let's see what we mean by that. So when are the ReLUs active here? By active, we mean they let their input through instead of setting it to 0. Well, for that to happen, their input has to be positive. For the first hidden variable that follows this expression, you can work it out on your own. This happens if the day is smaller than 351 plus 1.32 times the hour. If that happens, then the ReLU is active because its input is positive. It just lets its input through. What about the second one? Well, the second hidden variable is given by a different linear combination. In this case, this is positive if the day is smaller than 206 minus 0.12 times the hour. So it just so happens that the hour is positive for our problem. So this guy is always smaller than this guy for the kinds of inputs that we're interested in. In particular, this means that if this guy is positive, well, that's a terrible, there you go. If this guy is positive, then they're both positive. So if the day is smaller than 206, both ReLUs are active. Both ReLUs are letting their input go through, which means that the network is implementing the following function. So we can now just let the two ReLUs, we can just ignore them. They're just letting their input go through. And if we compute this out, if we replace H1 by a linear combination of the hour and the day given by that linear combination that we saw before, and the same with H2, and then we multiply them by these other linear coefficients and add, this is a little bit tedious, but you can do it. You end up with the following function that relates the output of the network to the input, which is affine. This only happens if the day is smaller than 206 minus 0.12 times the hour. When that happens, this is the function that is implemented by the network because the two ReLUs are active and are letting their input go through. Now what happens if the day is larger than 206 minus 0.12 times the hour, but smaller than this other quantity? Well, we saw that the first hidden variable is positive if this happens. The day is smaller than 351 plus 1.32 times the hour. The second one is negative if the day is larger than 206 minus 0.12 times the hour. So in this case, the second hidden variable is going to be set to 0 by the ReLU, and only the first hidden variable is going to survive. Okay, in that case, only the first ReLU is active and letting its input through. The other one is going to cut off that input, well, cut off that hidden variable, set it to 0. In that case, the network is going to be equivalent to this, where we can just take the first hidden variable, write it in terms of the hour and the day, multiplied by 4.76 at 0.22, and then you get this new expression for the output of the network in terms of its input that is only valid under this condition. And it's completely different to the one we obtained before. So the function implemented by the network is completely different depending on the input, which is exactly what we want in order to be able to implement nonlinear functions. Finally, what happens if the day is larger than 351 plus 1.32? Then the first hidden variable is negative, and the second hidden variable is also negative, because remember that we're interested in situations where the hour is positive. So then this guy is smaller than this guy. Okay, so this means that both of the hidden variables are going to be negative. Neither is going to be able to pass through the ReLUs. Both ReLUs are not active. They just set their input to 0. So the whole network is just equal to 0.22, which is the additive constant that we add to the linear combination of the two rectified hidden variables. So as a summary, the function implemented by the neural network is an affine transformation that adapts to the different inputs. And the way it adapts is as follows. If the day is smaller than 206 minus 0.12 times the hour, then we get this guy. If it's larger but smaller than this other value, we get this guy. And if it's greater than 351 plus 1.32 times the hour, we get this third value. And now realize that the linear dependence between the temperature and the day completely changes depending on what time of the year it is. So at the beginning of the year, the temperature increases with the day exactly as we want, but later on, it actually decreases with the day, which is also what we want after the middle of the summer. If I draw the regions where these two affine transformations are valid in terms of our input space, our input feature space, we see that at the beginning of the year, when we know that the temperatures are increasing with the day, indeed, the temperatures are increasing with the day, and the neural network implements exactly that. During the fall, well, the end of the summer and the fall and the beginning of the winter, it does exactly the opposite, and the temperature decreases with the day. So it manages to learn this nonlinear structure that we could not learn with the linear model. This is what the temperature estimates look like for the different possible values of the hour of the day and of the year. This is a very simple network. So it essentially just learns that at the beginning of the year, temperatures rise and then they decrease. But still, this is very important structure that is useful to that is very useful to estimate the temperature from these two features. And in fact, the training error now goes down to 6.32. And the test error is also very good. It's 6 degrees compared to the linear model that didn't capture this nonlinear structure that had a training and test error of 11 degrees. So this shows that this very, very simple neural network is able to capture this nonlinear structure that the linear regression model cannot capture. And this enables it to fit the data much better in a way that generalizes to the test data. Okay, so we have analyzed a network that had already been trained, but now we're going to learn how you actually train a neural network. The idea is that we need to learn the parameters in the network, which are the weights and biases, the biases are just the additive constants of the linear layers. And we want to do this from a training set that has feature vectors and the corresponding responses. This is the same setup that we discussed when we were looking at linear regression or at regression trees or at tree ensembles. And in fact, we're going to minimize exactly the same cost function that we minimize when we fit an ordinary least squares model or when we fit a regression tree. The key difference is that the model that maps the input features to the response estimate is very different. Now it's implemented as a neural network like the one I showed you before. And basically the idea is that we take this cost function and we try to minimize it. Minimizing it is not obvious because this is a non-convex function of network parameters, so we're not guaranteed to converge to a global minimum or anything like that, but we do it anyways, and you often get very good results. The general strategy is to minimize iteratively via some variant of gradient descent. In particular, a problem that you usually run into is that you want to use large data sets, which make it very difficult to compute the gradient of the whole cost function with respect to all the parameters. In order to address this problem, the fact that the training sets are usually too large to just apply standard gradient descent to try to minimize the residual sum of squares of the error. The solution, I got a bit lost there, sorry about that. The solution to this problem is to separate the training data into subsets or batches of smaller size. And what we do is we consider the residual sum of squares, which is just the sum of squared errors within the batch. So for the MB examples of the batch, we compare the response to the estimate produced by the network when we input the corresponding features. We do that for each individual batch. We compute the gradient of the network parameters, which are all these linear coefficients that we talked about before and the additive constants with respect. So we compute the gradient of the residual sum of squares with respect to those parameters. And then we go down that gradient little by little, where basically this constant essentially tells us how much we step in the direction of minus the gradient to try to decrease. That's how gradient descent works, to try to decrease this cost function little by little. That constant is called the learning rate, and it's crucial to adjust it properly, because if you go down in the direction of minus the gradient too slowly, then you will take very long to obtain a good model. And if you go too quickly, you might diverge. You might not actually minimize the function because the gradient yields a linear approximation to your cost function that is only valid close to that point, if that makes sense. It's often very useful to use methods that adapt the learning rate as you're tweaking these parameters to minimize the residual sum of squares. And a very popular option is ADAM, which is what we use in our experiments. This is called stochastic gradient descent because you can see this gradient as a stochastic approximation using a random subset of your data, because these batches are usually obtained by randomly sampling your training set. You can interpret it as a stochastic approximation of your whole gradient. This is what happens when we train our small neural network. This small neural network cannot really overfit the data because it has a small number of parameters, and because of that we see a training error and a test error that is almost the same as the network is trained. I mean, here you see that the training error is slightly smaller, but it's very, very similar. And you can see also that it takes around 500 epochs to convert. An epoch is when you have used all the batches that compose your whole training set. So when you have seen your whole training set. Here we have taken gradient steps over 500 epochs, which means that we have seen each data point 500 times. Okay, hopefully that makes sense. Now that we have seen what the model does and how we learn it from data, we can consider how to improve it. And the way to improve it actually is a good example of a very, very important philosophy in modern deep learning, which is just make it bigger. Make the network deeper, add more layers, add more hidden variables, add more parameters, and this hopefully will allow you to capture more information from your data. So we're going to use a 4-layer network. This 4-layer network is going to have 100 hidden layers instead of just 100 hidden variables. 100 hidden variables instead of just 2. So this second layer is going to map from 100 variables to 100 new hidden variables. The third layer is going to map from 100 hidden variables to 100 hidden variables. And finally, we take the last 100 variables and we collapse them into a single estimate. And in all the layers, we have additive constants for all the hidden variables and for our final output. So this network, as you can see, is massive with respect to the original network. In fact, if you look at the number of linear coefficients, for example, in the second layer, it's 10,000 coefficients plus 100 additive constants. Same for the third layer. So there's many parameters within this neural network. Okay, the neural network parameters, again, are the linear coefficients for each of the 4 layers and the additive constants for each of the 4 layers. Between each layers, by the way, we're always going to put a rectifying nonlinearity, which is indicated by this plus here. So we perform these linear transformations, and always each hidden variable is going to go through a rectifying nonlinearity, except at the very end where we want to be able to output negative temperatures. So here you might be very troubled unless you're used to deep learning. And in fact, this is something that was really bothering statisticians about deep learning at the beginning. Here the number of data are 8,760, okay, because this is the number of hours in a year. But the number of parameters in the 4-layer neural network, because of this, essentially mainly because these 2 intermediate layers that have like 10,000 linear coefficients each, the total number of parameters is 20,601, which is way larger than the number of data. So we're over-parameterizing. We have more parameters in our model than the data that we're going to use to learn the model. This, again, was shocking to statisticians, but it's prevalent in modern deep learning. Large vision models have up to billions of parameters, and obviously there are not billions of data points, and large language models can have up to trillions of parameters. So this is quite incredible. So a statistician would ask, yeah, but then what about overfitting? Especially for our problem, because these large vision models and the large language models are trained with, like the large language models are trained with the whole internet. So the data sets are extremely large. Not as large as the number of parameters, but it's extremely large. And we have a small data set. In fact, it's a good analogy anyways, because our data set is small with respect to the number of parameters, and that also happens for large language models and large vision models. So what about overfitting? Let's take a look at our training and our test error for different epochs and realize that here we're training for quite long. This is 1,000 epochs. By this time, we've seen the data 5,000 times. So what we observe, and by the way, you should never do this with your actual test set. You should do it with held out validation data, but I just wanted to keep things simple. What we observe is that the training error goes down and the test error also goes down, but eventually goes up again. So we do observe overfitting at the end because of the fact that we have so many parameters with respect to a number of data. But the key question is, what happens here? Do we get a better model? And we actually do. So here we can compensate for this overparameterization or overfitting by performing early stopping and considering the model that has not overfit yet. There are other strategies to try to prevent overfitting in neural networks, some of which include regularization that is similar to the regularization that we talked about in rich regression for the linear coefficients within the layers. That's called weight decay. So it turns out that for our example, early stopping mitigates overfitting. This is the model that we get at epoch 5,000, and what we see is that we have overfit some structure here. It doesn't make a lot of sense that here it's warm and then suddenly it's cold. We're overfitting the fluctuations in the temperature that were observed in 2015. And in fact, this gives you a good training error, but the training error the test error actually is not that bad because you're also capturing a lot of structure that allows you to fit the data quite well in ways that generalize reasonably well to the test data, but you're overfitting. We can see it there. In the first epochs, in particular in epoch 300, we overfit much less. So we fit the training data less well than at the end of training, but the test error is better. We generalize better. And when we compare this to the small neural network, we do pretty well. Notice that here, even despite the overfitting, we are learning enough useful structure in the data to do as well as the smaller network, even though we're clearly overfitting. So sometimes overfitting is not that problematic if eventually you get good results on held out data, even if they're not as good as in your training data. That's something else that is a little bit counterintuitive about this deep learning paradigm. But anyways, the point is here that early stopping does help. You do have to be careful with overfitting in many situations when applying deep learning models. Here, we prevent it by stopping the model when we realize that here we would use a validation held out dataset to decide when to stop. When we realize that the held out validation estimate is going up, it's becoming worse, and this enables us to get a much better test error. Now, we spent some time analyzing what function was implemented by this simple two-layer network, and we realized that first temperature was increasing with the day of the year, and then it was decreasing with the day of the year, which made a lot of sense, and so on. Now let's take a look at what the four-layer network implements. So we can take the same approach and see when the different ReLUs are activated. And for that, we have to ask ourselves, how many ReLUs are there? Well, there's one for each of the hidden variables at the end of the first, second, and third layer. There's 100 hidden variables in each layer. There's 300 rectifying nonlinearities. How many possible activation patterns are there among those 300 ReLUs? Maybe, stop the video and think about it for a moment. It's going to be 2 to the 300, right? Because each of them can be activated or deactivated. So this gives you 10 to the 90 different possible affine functions that can be implemented here. So good luck, go list them and take a look. It's completely impossible. So we have better performance, but we have absolutely no idea what the network is doing. I'm exaggerating, right? Like for specific inputs, we can always look at the linear, at the affine function that is implemented by the network, but we have to fix the specific input. We cannot say in general what the network is doing. And this idea of fixing the specific input and looking at essentially the function that is implemented for that specific input is actually how you get, I'm saying actually way too much, sorry about that, is how you get activation maps in computer vision. Not activation maps, I got that wrong, sorry, saliency maps is what I meant. Not activation maps, saliency maps, which tell you what input pixels in an image are used by the network to determine whether the image is a dog or a cat. The issue there is that you can only get these saliency maps for that specific image. You cannot say in general what features are being used to classify dogs against cats in general. That's what I mean here. And the reason is because there's so many nonlinearities within the network that can have so many different values that it's just not tractable to consider them all. And in fact, the whole point of using deep learning and neural networks, I'm going to go back for a moment, is that you're actually implementing complex nonlinear functions that enable you to perform estimation really well. This is the whole point. So in a way, you're losing interpretability just because these models are so complex that we cannot really understand them very well anymore, but they yield good performance. Now we have explained how to use neural networks for regression. I'm going to briefly explain how to use them for classification. And I'm going to use this example where we want to classify wheat varieties that are Canadian, Kama, and Roma. So we have 3 varieties from 2 features, which are the asymmetry coefficient and the area. Notice that here the Canadian wheat seeds are more asymmetric, have less area. The Rosa wheat seeds have more area, less asymmetry, and for the Kama variety, the asymmetry coefficient and the area is small. Both of them are small. Notice that the features are standardized by removing the sample mean over the whole data set and dividing by the sample standard deviation, which is why we have negative areas, in case you're kind of wondering that why on earth we have negative areas. Okay, so we want to perform classification here. We have this data where these are the features and these are the labels. I want to fit a classification model that is able to identify which of the 3 classes in our example corresponds to new data points. Each feature xi is a d-dimensional vector. The label indicates the class, whether it's Canadian, Kama, or Rosa in our example. And our goal is to assign a class to new data. And in order to do this, we apply probabilistic modeling and we model the features as a random vector x and a random variable y. And realize that this is exactly what we did when we were discussing softmax regression and also classification trees. For a new data vector x, the optimal thing is to just compute the conditional probability of the class given the features and choose the class for which that probability is higher. So this seems like a solved problem, but again, because of the curse of dimensionality, exactly like in regression, you cannot approximate the conditional mean. Here we cannot approximate this conditional probability because there's just too many possible values of the features. Because of that, we have to make assumptions. In order to perform discriminative classification, what we do is we make certain assumptions to approximate this conditional probability of the class given the features. We discussed this in detail in the logistic regression video, in the softmax regression video, and also in the classification tree video. For logistic and softmax regression, what we do is we take a linear function of the features and then we map it to probabilities with a nonlinear link function, which is the logistic function for logistic regression and the softmax operator for softmax regression. In the case of a neural network, we're actually going to do almost the same, except that instead of inputting a linear function of the features, we're going to input a nonlinear function of the features implemented by a neural network like the ones I showed you before, and we're going to map that to probabilities. So how does this neural network classification work? Let's compare it to softmax regression. In softmax regression, we take these linear estimates, they're actually affine because they're additive constants, of these linear functions that we call logits of the input features, and then we plug them into exponentials, we make them more extreme, and then we normalize them so that the maximum value is going to go towards 1 and the smaller values are going to be pushed towards 0. We discussed this in a lot of detail in the video on softmax regression. Well, what do we do with a neural network? We do exactly the same thing, except that these C logits, where in our example this would be 3 logits, one corresponding to each class, are not generated with 3 different linear combinations of the input features. They're generated with a neural network that performs this complicated interleaving of linear functions and nonlinearities to produce these 3 values. The output of the whole network is not going to be just one output as in regression. It's going to be these 3 outputs that are the logits. And then those logits are going to be put into a softmax that is going to generate the 3 corresponding probabilities by feeding them through an exponential that is going to produce extreme values pushed towards 1 or 0 if one of the 3 logits is greater than the others, exactly as in softmax regression. Okay, maybe that got a little bit complicated. The point is we apply this softmax regression operator instead of to these linear logits, to the nonlinear logits obtained with a neural network. How do we learn the parameters of the neural network? This is not going to come as a surprise, I guess, because we're going to do exactly the same as we did in softmax regression, in logistic regression, and in classification trees. We're going to try to maximize the conditional likelihood of the labels with conditional likelihood of the labels given the observed features. So we model the features and the labels as random variables x and y, and then we consider the conditional probability of the actual observed values. So just to be clear, the observed values are these guys, and these are the random variables that represent the labels, given the observed values of the features. Now we have to make assumptions in order to obtain a likelihood that is tractable to maximize, and what we assume is that the labels are conditionally independent given the features. So now this conditional probability can be factorized into the conditional probability of each observed labels given the observed features, and we're also going to assume that given its own feature, so for example for y1, given that we see x1, we don't care about the other features. So essentially we're assuming that each of the examples are independent in a way, if you want. If that happens, then the whole likelihood simplifies to just the product of the conditional probability of each label according to the model, given that observed feature. This is exactly the same as we did for logistic regression, for softmax regression, and for classification trees, except that now the model is actually a neural network that is fed into a softmax operator. And that gives us these estimated probabilities corresponding to each of the training data points. And we're going to maximize this whole likelihood with respect to the network parameters, which are these linear coefficients that are inside the network. The softmax operator doesn't have any parameters. The rectifying nonlinearities also don't have any parameters. This is all about setting the linear coefficients within the network. This is what the likelihood looks like. Usually we use the log likelihood because the likelihood is obtained by multiplying a lot of probabilities which are very small numbers. So in order to get numerical stability, we consider the log likelihood. And this is maximized via stochastic gradient ascent. So now we're going to use batches to follow the gradient upwards and try to maximize the likelihood as much as possible. Exactly the same as we were doing for the residual sum of squares, except that with the residual sum of squares, we wanted to minimize it. This cost function, this log likelihood cost function, if we put a minus in front, can be interpreted as the cross entropy between the empirical probability observed in the data and the conditional probability is computed by our model, and that's why it's often called the cross entropy loss in deep learning. Now let's take a look at what happens if we apply this to our wheat varieties. This is what the linear logits for the first variety look like if we apply a softmax regression model where the input to the softmax is linear. So as you can see, like the relationship between the logits and the two asymmetric coefficients are linear. These are the contour lines of the logits where their value is constant. Here they're equal to 4, here they're equal to 8, and so on. This is the resulting probability estimates, which are quite regular, right? They're constrained by the fact that there's a linear function going into the softmax operator. Now these are the nonlinear logits learned by neural networks. They're much funkier. These are the contour lines. As you can see, they don't follow straight lines anymore because now the neural network can do what it wants and capture very nonlinear structure. When we put this in through the softmax, we realize why there's this weird thing going on here. There's this weird thing going on here because the network is able to assign high probability to this Canadian data points while assigning low probability to these gamma points that are in between. Here you could probably be worried about overfitting. I'm just trying to show you the power of the neural network to capture nonlinear structure with respect to the softmax regression model. It's actually possible that here we're just overfitting. Okay, but this strategy of trying to capture as much structure as possible when you have a lot of data has been spectacularly successful in many problems. What happens with the second variety? These are the linear logits in softmax regression. Again, they're linear. The corresponding probability estimate is constrained by that. For example, it cannot assign high probability to this guy. This is not a problem for the neural network that just goes bananas and computes these very complicated nonlinear logits so that it can assign low probability to these guys while assigning high probability to these guys and get essentially zero errors for this training set. Again, we're probably overfitting here. I'm just showing you the ability of the network to adapt to whatever intricate patterns it finds in the training data. Finally, same thing for the last class. These are the values of the linear logits that give you like this, like these very regular shaped probability estimates. And the nonlinear logits are much funkier because, for example, they want to assign probability of 1 here while assigning a low probability to this point here. So they're able to adapt to the data in an extremely flexible way. So what have we learned? We have learned how to build nonlinear regression and classification models using neural networks. We have learned about the general framework used to train neural networks, which is to separate your training data into batches and perform stochastic gradient descent. We have learned about the power of overparameterization, where we use deep neural networks that have many, many parameters, potentially more than the training data points that you have, in order to be able to capture intricate patterns in the data. And we have learned that we have to be careful about overfitting and always monitor how our neural networks are doing on held out data. And that's all I got. Thank you very much.